Greetings hackers, Dimitris from zSecurity here, and today we're diving into one of the most notorious and foundational vulnerabilities in software security, called buffer overflows. This vulnerability has been around for decades, causing chaos into countless systems from old-school terminal programs to modern-day applications. But what exactly is a buffer overflow, and why is it such a big deal? Let's have a look. Before we dive into today's video, I'd like to give a shout out to our sponsor, ANY.RUN. ANY.RUN is a cloud-based sandbox specifically designed for interactive malware analysis. It lets you dig into cybersecurity threats with full control, providing real-time interactivity as if the suspicious file was right on your desktop. You can click links, open files, and even reboot the system to get hands-on with your investigation without worrying about infecting your own machine. One of the best parts is that you can get started in seconds. Set up your environment to match specific locales and even use OpenVPN to get the most accurate results in a secure, flexible setting. You can rerun tests as many times as you need, so you get instant access to results, making malware analysis faster than ever, and with no limit. As you can see, ANY.RUN is designed for experts and beginners alike, with no extra hardware required. You can sign up for free using the link in the description or make the most out of their Black Friday discounts and go for the heavily discounted Hunter and Enterprise plans to unlock all of these advanced features. Alright, let's break it down. Imagine you've got a box, and this box represents a buffer in memory. This box is designed to hold a specific amount of data, let's say 3 items. Now, when data gets put into this box, everything is fine as long as you stay within those 3 items. But what happens if you try to cram 7 items into it? Well, you overflow the box and extra data spills over into areas of memory that weren't meant to store it. Now, this is where things get messy. In computer terms, a buffer is a chunk of memory set aside to temporarily store data. A buffer overflow occurs when a program writes more data into the buffer than it can actually hold. Since memory is tightly packed, overflowing data can overwrite adjacent memory locations, which often include critical information like return addresses, variables, and other program data. Let's see an abstract example of how an overflow can occur. Say we have this buffer space of length 8, which means that we can only store up to 8 bytes into this memory. Adjacent to it, we can see another memory location that stores other program-related data which must not be tampered with. We can see that the string test123 can easily fit inside our buffer. But what happens when we try to store something into the buffer which is larger than 8 bytes? We overflow into the next memory location, and this can cause a lot of trouble. You can see, for example, that password123 is not small enough so that it can fit inside the 8-byte buffer space. That is why 123 is written into the adjacent memory location that we talked about earlier. So if you recall our previous example with the box and the items, the extra items that are added to the box are this 123 over here, and that's exactly what spills outside of our little box. So basically the data that was here previously was overwritten by our input data, and that's the overflow. Here is where the danger comes in. If an attacker can control the overflow data, they can manipulate what gets written into memory. This can lead to all sorts of malicious outcomes, from crashing the program to executing arbitrary code. Basically, you hijack the program's execution flow, tricking it into running whatever code you want. We will later see how we can control the return address to redirect execution to malicious code. In simple terms, the program thinks it's processing harmless data, but in reality it's being fed malicious instructions that can lead to a full system compromise. All this is a very high-level overview of how everything works though. Let's see it in action to get a better understanding. We will be using a vulnerable binary to demonstrate how buffer overflow can occur. It runs on Windows hosts, so for this attack we're gonna need a Windows target and a Kali attacker machine. We first need to set up our environment and install the necessary tools. Let's download our vulnerable binary called vulnserver from this link. All of the links shown here can be found in the description of this video. So in order to download the file, simply click on this green button here and then download zip. I've already downloaded this file into my desktop, so I'm not going to download it again. In order to monitor the execution of our vulnerable binary and to understand how we are going to exploit it, we're going to use a debugger. For this video, we will be using the immunity debugger, so let's go ahead and install that too. Simply click on this button and save the exe. We're not going to show the installation process here as it's a very simple process. You just need to click next, next, next on each prompt and you should have immunity debugger installed after that. Debuggers can help researchers and attackers identify points in a program where buffer overflows can occur. They allow step-by-step analysis of how data is being handled, such as input validation or buffer management, which is key to locating exploitable vulnerabilities. Now, the last thing we need to do is to install a plugin to the immunity debugger called Mona. This will help us during the exploitation phase. We will simply download the file and save it to our desktop. I already have it here, so I'm not going to download it again. And then we'll need to add it to Immunity's plugin directory. So to do that, we can simply take the file, open a file manager, and it's very simple to find the plugin directory for Immunity Debugger. Simply go to this PC, your C drive, program files x86, Immunity, Immunity Debugger, and then inside py commands, you should be able to paste the mona.py plugin. And now that's done. Now that everything is set up, we can begin testing the binary. Let's first extract it from the zip file. And we have the vulnerable binary right here. Let's first launch it normally and try to use it as a regular user. This opens a server that's running on port 9999, which we can connect to from our Kali machine using a tool called netcat. So let's go back to our Kali machine, to a terminal, and let's use netcat to connect to the server. I already know the IP address of my target, but if you don't know the IP address of your target, simply head to a terminal and type in ipconfig. And you should see the IP address of your target right here. So what this command basically does is say that, hey, I'm trying to connect to this IP on this port. So let's try to run that. And as you can see, we got the welcome message saying that we should enter help for help. So let's do that. We can see here a bunch of commands that we can send to the server, but I don't want to waste your time. I already know that the run command is vulnerable to a buffer overflow, so we're going to try to hack that. But what does the run command do? If we execute it with an input, it simply just says run complete, which signifies that the operation completed. Then what is the issue with this run command? Let's check out the code to see what's wrong with it. This code is written in C, but you don't really have to know the C programming language to understand what's wrong here. I've added these comments to show you where the vulnerability appears. The problem with the run command is that it does not properly check the size of the user input. It tries to copy up to 3000 characters of input into a buffer, then sends this input into another function over here, and that function copies it again into a smaller 2000 character buffer using a risky function called string copy. If the input is longer than 2000 characters, it will overflow the small buffer. This can cause a program to crash or allow an attacker to run malicious code, making it a serious security risk. So there should have been something inside function 3 that would check the size of the input, and if that was larger than 2000 characters, it wouldn't have gone inside the string copy command. And this is where the vulnerability gets introduced. So we know now that the input that exceeds 2000 bytes will cause an overflow, but in a real-life example, you probably wouldn't have the source code for the program you're testing. That's why we will demonstrate how to figure out how many bytes it requires to cause a buffer overflow using what's called a fuzzer. A fuzzer is simply a tool that connects to the server similar to how we did using netcat, and it sends data every some interval. Each interval, the size of the data is increased in order to find out which amount of data will cause the program to crash. So think as if you were to manually connect to the server each time and trying to increase the amount of bytes you're sending to the server. This just does it automatically. You can use the fuzzer code found in the description of this video. So you can simply download it from clicking this file and saving it into your downloads directory. I already have it in my root directory, so I'm gonna use it there. So let's exit from this netcat connection we created before and clear our terminal screen. Let's also terminate the vuln server that we ran manually before so that we can actually start it from the Immunity debugger. So let's launch Immunity debugger. So this is the program that's gonna help us understand what's wrong with the vulnerable server binary, and it will also help us during the execution phase. This program might look overwhelming at first, but don't worry, we're gonna be explaining everything that we do. And from here, click on File, Open, and open the vulnerable server. As you can see, it says right here that the program is now paused. So the first thing we need to do is to actually click on this little button here to continue the execution of the vulnerable server. And as you can see, now it says running. We're mostly gonna be playing with the registers plane over here, as this is the most important part for this demonstration. Let's go back to Kali and see if we can set up our fuzzer. So I've actually opened the fuzzer.py file from leafpad over here. You can use any text editor you want. And I went ahead and pasted in the IP address of our target. This is the only thing you need to do. Our fuzzer program is really simple. We're first declaring the IP address of the target and the port. We are setting an initial value for the amount of bytes that we're gonna send. Then we start the connection to the target server. And inside the while loop, we are creating a payload that we are sending repeatedly every second. So every second, we are increasing our payload size by 500. And we are hoping that eventually the program will crash due to a buffer overflow. So now that we know how the fuzzer works, let's run it. Let's go back to the terminal and run Python 3 fuzzer.py. So it's sending the bytes right now, and if we go back to Immunity, you will see that after 2200 and around 2700 bytes, we got the program to crash, and we can actually see the overflow. Have a look at this EIP register over here. As you can see, the address that this register points to is 41414141, which is the hex encoding of the letter A 4 times. We were able to overflow our data inside the EIP register, and this is very crucial. Controlling the EIP register, short for Extended Instruction Pointer, is crucial because it dictates the next instruction that the CPU will execute. When an attacker manipulates this register during a buffer overflow, they can redirect the flow of the program to execute the malicious code. In essence, gaining control over the EIP register allows the attacker to hijack the program's execution, turning what once was a simple software bug into a full-blown security exploit. So this right here is the key to what's going to allow us to redirect the execution flow of our program and then allow us to run an exploit on the target machine. All of this is very cool, but how do we know where exactly those A's are in our input so that we can know exactly at which point we should enter our malicious input to control the EIP register? To better visualize this, think that this buffer has X length. Once the buffer overflows, the rest of the data gets put inside the EIP register. We will need to find exactly after how many bytes we can start putting data inside the EIP register. That is the X value. For that, we can use a tool built into Kali called MSF pattern create, which generates a unique set of characters of a specified length. I'm gonna clear my screen first, and then I'm gonna run MSF pattern create. Since we know that after about 2000 bytes the program overflows, we can use 2300 bytes just to be sure. So in order to specify the length of our unique string, we're gonna do -L and then 2300. Let's run that. And here is our unique string. Now that we have our string, let's copy it and send it to the server. But first, we have to restart the program on our debugger, since we previously crashed it. To do that, we can head back to the Immunity debugger, click on Debug, and press Restart. It's gonna ask us if we want to terminate the process. We're gonna say yes. And now the program has restarted. Make sure you also resume the execution of the program using the play button from the top, like we did before. So again, what we're trying to do right now is to try to understand after how many bytes we can control the EIP register. So let's get back to Kali, clear our screen, and let's connect back to our target using netcat. Same command as before, we're simply connecting to the server IP using the port 9999. We get the same welcome message as before, but we don't need to run help this time. We know what to do. We're gonna run run, followed by these characters here. These are very crucial to add as it helps the program understand that we're trying to do the overflow. It's just the way the developer coded the vulnerable server. And immediately after these characters, we can paste in our unique string. We can press enter. As you can see, the program crashed again. And now we can use what the EIP register points to figure out how many bytes we need to use to control it. So let's copy this text with right-click copy selection to clipboard and use it in another built-in tool called MSF pattern offset. So let's get back to Kali, terminate this connection with Ctrl+C and run MSF pattern offset. We again have to specify the length as 2300, and this time we also have to add what the EIP register was pointing to, and we can paste that right there. So this command will tell us exactly after how many bytes we can control the EIP register. And as you can see, the exact match for this offset is 2003 bytes. That is great. We're slowly acquiring all the necessary information needed to exploit the program. The next thing we need to do is to find a way to actually redirect the execution of the program. We can do that with the so-called jump instructions. The jump instructions in assembly code allows the program to jump between addresses. Let's first restart our program again. To find these jump instructions, we can use the Mona plugin that we installed earlier by running the following command on the terminal at the bottom of the screen right here. So click on the terminal screen and write this command down. This command will show us all the jump instructions we can use that also exclude the null byte. We exclude the null byte to prevent any sudden termination of the program. So let's hit enter. And we got the terminal screen to show us something, but it hid itself. So in order to find it again, we can minimize the screen from here. And there is the terminal. This is the output of the command, and as you can see, we have a bunch of results actually for jump instructions. I'm actually going to go for the first one, so I can click on it here, right click, copy to clipboard, and then select the address. Now we're almost ready to start constructing our final exploit. We first found exactly how many bytes we need to send to the server in order to start controlling the EIP register. And the EIP register, we said, is the one that points to the next instruction to be executed by the CPU. And controlling that will allow us to run our shellcode. Then we found a jump instruction that's going to allow us to actually redirect the execution of the program to run our malicious code. So in the place where the EIP register is going to be overflown, we're going to place the jump instruction that we just found to finally redirect the execution to our malicious code. Let's visualize what our exploit will do into the program's memory. We know that we have a buffer of 2000 bytes. After sending 2003 bytes to the application, we saw that we are able to access the EIP register. This is where our jump instruction goes. And this is where the overflow starts happening. After that, we continue with an OPSLED, which, like we discussed before, is basically telling the CPU to do nothing for 20 operations, because we're actually sending 20 no operation instructions. The NOPSLED acts as a white space between our malicious code and the rest of the exploit. And finally, after the NOPSLED is done, we enter our malicious code, which is then executed by the CPU. So this is a high-level overview of what our exploit will do to the program's memory. Let's have a look at our exploit to get a better understanding of what's gonna happen. This is the exploit code we're gonna use on the target. We're firstly supplying the IP address and the port number. Then we're setting the length of our attack, and I've set it to 2500 for good measure. The offset is going to be exactly how many bytes we need to send to the server to reach the EIP register. That's going to be 2003. And this EIP variable is going to be the jump instruction that we just found. Our malicious code will go here. Then we have an offset, which is basically telling the CPU to do nothing. NOP stands for no operation, and we're going to have 20 of these instructions to the CPU. This is going to serve as a white space between our malicious code and the rest of our payload. And here you can see us constructing the payload. We're starting with the same run command that we were running before. Then we're sending the amount of bytes we need in order to reach the EIP register. After reaching the EIP register, we're telling it to go to that jump instruction that we found. Then we have the no operation sled followed by our malicious code. And then we fill in the rest of the available space of the 2500 length with a bunch of C's. The key points to this exploit is the fact that we are reaching the EIP register, we're telling it to go to that jump instruction that we supply to it, and that jump instruction redirects the traffic of the executable to our malicious code. So you can use this code for the exploit, which is also found in the description, and download it similarly to how we did with the fuzzer. I already have that downloaded to my Kali, so I'm simply going to open it again on LeafPad. So let's start editing it. I'm going to start by adding the IP address of our target. The next thing we need to do is to add the offset. The offset was 2003. So after 2003 bytes, we are reaching the EIP register. Then over here in the EIP variable, we're going to have to delete address from here and then paste the address that we got from the jump instruction. Now all that's left for us to do is to generate a malicious shellcode that will run a reverse shell to our Kali. Shellcode is a small specialized code, usually in machine language, designed to execute something harmful, like opening a shell or granting access to the system. This code is then injected into the memory using the buffer overflow. To do that, we can simply run this command. Let's go over what it does. We're running MSF Venom, which is a tool used by hackers to generate payloads, and in this case we're generating a Windows shell reverse TCP payload. We're setting the L host and the L port, which is what the target is going to attempt to connect back to. Then with exit func equals thread, we're basically just telling the payload to cleanly exit after running. This is very crucial when it comes to exploits, as this can interrupt the execution of the payload. And then we're simply excluding the null byte like before. Remember, while searching for the jump instruction, we specifically told it to exclude the null byte to prevent any sudden termination of the program. We're following the same principle here. Now all we need to do is to actually change the IP here to our Kali's IP. I'm going to split my screen like this, run fconfig to find my IP address, and copy it from here. Let's paste it down. Another thing I forgot to point out is the fact that we're telling it to output the shellcode into a Python format. So we can actually use this shellcode by just copying and pasting it into our Python code. You'll see what I mean after we generate it. So let's run that and see what we get. As you can see, the command is now done. And like we said, it outputs the shellcode in Python format. So we can simply copy this and paste it on our exploit. This is supposed to go under here. And now we can save the exploit. So again, this right here is machine code, and all it does is tell it to actually connect back to our Kali machine and give us a reverse shell. This is our malicious code. Now our exploit is complete. If all goes right, we will redirect the execution of the program to run our shellcode, and then we'll gain a reverse shell to the target. Before we run the exploit, let's start a listener on port 4444 with the command nc-lvnp on port 4444. This command simply uses netcat to listen for incoming connections on our specified port. Let's hit enter. And the last thing we need to do is to actually restart the program on the immunity debugger. So let's get back to the immunity debugger, find the CPU page, and enlarge it. Let's restart the program. Don't forget to press on play, and now the program is running. Everything seems to be ready. Let's run the exploit and get that shell. Let's go back to Kali, clear the screen, and run python3 exploit.py. And there you have it. We have just gotten a connection back from our target, which means we successfully exploited the buffer overflow vulnerability. If we run whoami, you'll see that we are inside the Ictos computer. We were just able to remotely hack our target without having the need to actually send the target any malicious executables. All we did was exploit a vulnerable application that was already installed on the target. To wrap things up, buffer overflows are classic yet incredibly dangerous in the world of cybersecurity. As we've seen, by overflowing a buffer, attackers can take control over key parts of a program, like the EIP register, and redirect the execution of the program into their malicious code. This can lead to a full system compromise, as we saw earlier. That is why this vulnerability is so critical. In this demo, we walked through how to set up our environment, identify the vulnerability in the run command, and eventually exploit it to gain a reverse shell. Using tools like the Immunity Debugger, Mona, and Kali's built-in utilities, we systematically broke down the buffer overflow process from finding the vulnerable input size to constructing our final exploit. Now, while this might seem complex, it really boils down into understanding how memory is handled and how poor input validation can lead to these serious security issues. Hopefully, this video gave you a good overview of the steps involved and showed you just how powerful these attacks can be when done right. And that's it for today. If you found this video helpful, don't forget to like, subscribe, and hit the notification bell for more tutorials on cybersecurity and ethical hacking. As always, this is Dimitris from zSecurity. Stay curious, stay safe, and I'll catch you on the next one.